So we are now looking at dynamic data structures, that is, things which can grow. Now, dynamic data structures require more memory. They are slower, but they can grow. So that's the plus side of it. But also, this slide is not correct in the sense that it says there is often overhead costs. There is always overhead costs in both time. Well, it really does depend. Certainly in space, there's overhead costs for dynamic structures, always. And it depends. Like, for example, if we looked at the dynamic data structure from the tutorial last week, that's actually got roughly the same kind of performance as an array. It's just the cost is when we have to resize it. But otherwise, it's as good as using an array. Better because it's resizable. But what we are going to be looking at are what we call recursive linked structures. So a recursive structure is one where there is a node type, but each other node in the data structure is one of these fellas as well. And so we can think about it being recursive in the sense that a node points to a node, points to a node, points to a node, points to a node. So it's recursive in that sense. Now, another good practice that's worthwhile in this regard is to, when you're designing a data structure, now there's two options. One is we have these nodes where we have links going to the next node and so on, and the old kind of monolithic style was, okay, I'm going to put the data in the same structure as as I have the pointers to next and so on. Can you think of any problem with doing that? So we have something like, say, I've got perhaps not that one. Well, we have struct node, and inside the node we have struct node star next, and we have struct, and we have, say, okay, char if name len +1, char l name and then we have struct list, correct. And there is a principle in software development which is a separation of your data structure from application data. Your data structure shouldn't need to know about the application data, and the application data shouldn't need to know about the data structure. So in fact, what we do here is we might do struct person star data. And then we'll actually have somewhere else our struct person and the details of that. Yeah. Believe it or not, when I first came into teaching C in this course, there were big arguments amongst the teaching staff about which was the better approach. And it just seemed to me that having the data in your list means a list is stuck to being one kind of list. We will see, before the end of the course, we'll see a way we can actually write a list so that it can hold any kind of data. And if you're writing libraries and that kind of thing, you wouldn't be rewriting your list for every new kind of data. That'd be silly. Okay, so here we go. We're going to do a person list here where we have a pointer to the person data and a pointer to next. And this is our definition of a person. It's really just a dummy example. I think it's better to use something a little bit more complicated than an int, because ints are easy to compare with less than and greater than and so on, whereas a struct is more complicated. Just complicated enough to be a little bit closer to real world data. And that's important, I think. And then we've got this header structure to pass things around. Now, in a real world system, you may in fact be storing more than stuff about the list. So when we declare the list, we get this structure here, which means we get space for the pointer and we get space for the number of elements, but that's all, right? So any pointers, we don't know where they point unless we initialize them. Right? And we don't. So I guess something to think about is if you've got this structure here and you want to initialize it to be an empty list, what should you assign these things to? What values should you assign to these elements? Try not to give in to the temptation to malloc something when you've got nothing to put there. Just because you got this thing called malloc doesn't mean you always have to use it. You use it when you need to use it. Correct. We would set head to null. Yeah. Very common mistake, which is why I ask the question. I know, by and large, the kinds of mistakes you guys make. Yeah. So, a linked list is an implementation of a more generalized abstract data type called a list. Exactly, Ross. So a list whose first element is null is an empty list. So, what things then do you think we need to do with a list? Now, maybe cast your mind back. Those of you who actually... Okay, you want to be able to display the list. Cool. Remove elements. Initialize, add, remove, free. I'd say that's enough. Moving backwards may or may not be something you want to do with your list. In our case, for assignment 2 implementation, you're going to need to actually have be able to go backwards and forwards in the list and be able to make those changes. We won't be using backwards too much, mainly really so that we can append to the end of the list quickly. Sort, depending on the list. Okay, so here's my list of things that I reckon you want to be able to do with every list. Clean up the list, free all memory, initialize it to a known safe empty state. These are all things which you want to be able to do with every list. In fact, I would say we can generalize this more than that and say for any collection, we more or less want to be able to do these things. Yeah, modify. Yep, fair enough. Well, that's an implementation dependent criterion. Russ, maybe sometimes, maybe other times not. Certain data structures... certain data structures require that each element is unique. So if you think about a tuple in a database, that's certainly an example. That's a row in a database. And so on, yes. But that's something which is implementation dependent. I'm making no assumptions about that. But these are the things which should be implemented in the list module. So you'll find in the assignment there is a list module whose .c file is empty. Well, anything related to the list should be put in there. And the list should be treated as opaque. We don't know the internals of it. We don't need to know the internals of it when we're doing our modifications of the list. We ask the list to do them. We ask the list module, hey, can you add an item here? Can you delete an item for us? I don't need to know about the internal implementation. What's the advantage of that? Of not knowing about the internal implementation? Yep. So, for example, I go, well, actually, it turns out a linked list is not the best data structure to use here. I want to make this an array instead. Yeah. So this is about having consistent interfaces, and it's essentially, are any of you familiar with things like, for example, model view controller as a design pattern? Well, it's about separation of functionality. There's no reason why you wouldn't use this stuff in C as much as any other language. Yeah. In C, it's more considered an optional thing. You'll find a lot of code out there which is written really badly, where it has poorly defined interfaces and so on, and it takes an awful lot of work every time you want to change something. I want the code you write to actually be better than that. I want you to be using consistent interfaces, and so when you come to debug your program, you know where the problem is likely to be. You can easily narrow down the problem, fix it, move on. Okay. I've already covered that one. Okay. Now, it's your responsibility as a programmer to manage memory. Now, I've actually got a linked list here. Let me just show you. Oops, no, how? Let's go for here. Oh, yeah. So I've got a program here, person list, right? So I'll just run it. We'll come back and have a look at the actual functions a bit more detail in just a moment. Okay, basically what it does is it asks for details about a person. So I'll put in my first name, last name, age. That's not my real age. And then okay, so I've now added 3 people, and I'll just press enter to quit. Oh, can anyone see the problem? At the end here, it's printing out the list as it's found it. What's the problem? Correct. And so what's actually happened is that there's a bug in my program. So if I have a look at my make file here, we will talk about make files in a bit more detail, I believe, week after next. Plenty of time for you to submit. But so you don't necessarily need to work on make files just yet. But okay. The important thing is I've got this -G here so that I can debug using Valgrind and GDB. Okay, so I'll just type make. Okay, it's all, there's nothing I need to do. So now Valgrind person list. Okay, so I'll do the same again. Now keep in mind this is actually sorted by name, this list, right? So, and here we go. Valgrind gives me information. It says personlist.c line 40. Okay. Now, I want more information. So I'm going to track origins equals yes. Okay, now here it says that we have a conditional jump or move depends on uninitialized values, which means there's an initialized value that we're using on line 40, right? And it's something which was declared in the function listAdd. So it's one of the variables I declare in this listAdd function, which is not initialized at the time it's used, of its first use, on line 40. Rightio. So it's line 40 of list.c, line 40. Okay. This is a common mistake that many of you make when you're initializing a list, is you forget that the previous pointer must be set to null at the start. We'll get into this a bit more later, but that's the problem. Okay. And now we get all three. There is still a problem where there's some memory which has not been freed, but we'll come back to that. That's what this means here. There were 6 allocs but only 3 frees, so there's something here I'm not freeing. So that there's still an issue there. Okay. So yeah, to use Valgrind we do the -g thing. Yep. So a linked list is sequential and linear. Right? You've got links going all the way along, except they're not necessarily sequential in memory. What do I mean by that? They're not necessarily sequential in memory. Correct. Each request for malloc, or new in other languages, is a heap allocation. Yeah. And it may be anywhere on the pages we have, or if we've run out of space on the memory pages for this process, we'll get another page. The operating system will allocate us another page, and it will allocate some space there. And it'll try to find a contiguous block. So a block which is next to each other, which is as big as the space we've asked for. So what it means, I'll just show you very quickly. Rightio, let's just say this is some heap space we've got. So the beginning of this line here is one alloc, then we have a second alloc, and we draw a link between them. And we do another alloc. We do another alloc. We do another alloc. So these lines are the links between the list nodes. So that's what our linked list might actually look like. Not pretty. And what else can we say? If we've got in our hands, we've got a list node, can we make any inference about where the next list node will be? Well, we follow the link, but we don't know how far away in memory. But the point is, though, when I ask for a new list node, do I know where that will be? No, and what this means is that while linked lists are a good data structure to learn about, and they're an entry point into your knowledge of data structures, they are not very predictable in terms of allocation, and for that reason they're not recommended as a high performance data structure. They're not a high performance data structure, but they're a good place for us to start learning about data structures. So adding an element at the right place in the list means searching through the list to find the insertion point. But the advantage we have over, for example, arrays, which we used in assignment 1, is we don't need to shift everything else down. So that's a plus for us. Just change the pointers. Now, I'm going to show you just a little bit from this video because I think it's a worthwhile video to look at. This is Bjarne Stroustrup, the inventor of C++. The issues he's talking about are the same as C, so that's not a big issue. But
algorithms. Here I'd like to show an example that first was shown to me by John Bentley of algorithms fame. Make a sequence of random integers, keeping them in order, and so you're given the numbers 5, 1, 4, 2, and it builds up the sequence as you see it there. And then you remove them again by giving a set of positions of which one you take out. And so the exercise is, for which n is it better to use a linked list than a vector or an array? And everybody gets this one wrong. Here's my graph has disappeared. This is embarrassing. Okay. Okay. So, imagine this to be a graph. The imaginary low line down by the bottom showing efficient usage, little time, is the vector. The one that is looking like an exponential trying to go through the ceiling is the list. And trying to figure out why the list is so inefficient, I thought maybe it's all this allocation that's been done for the nodes. So the little middle green line, which you can't see either, is the lists with allocation taken out, totally pre-allocated. The point here is that the vector is always better than the list, and the list gets worse the further you go out. And this is for the case where you're doing a lot of insertions and deletions, which, when I was taught about data structures, was what you use lists for, because they're really good in inserting, deleting. If you want to insert in the middle of 100,000 integer vector, you have to shove on average 50,000 elements one position. If you take one out, you have to shove them roughly half the way back. Now, this is completely irrelevant. What matters is the linear search to get to the insertion point. Of course, you have to go through half of the list to find the average insertion point for a list, and in an attempt of fairness, I also did the same for vectors instead of using a binary search. But anyway, so the linear search dominates completely. And linear search for vectors, it's not actually such a good idea. First of all, a vector is, for a list is much bigger for a given data structure than a vector, because you don't have to just store the element, the integer. You have to store the 2 pointers forward and backwards. You have to use a doubly linked list if you're inserting, otherwise you have extra problems. And that completely dominates. So the graph here, this graph here that you can't see.
So you can have a look at the rest of that at a later time, but it gives you a bit of an idea of some of the issues with linked lists, but they are a simple data structure, good for us to learn as a starting point. Yeah. Okay. And okay. Let's get back to our slides. Okay. So, on the next few slides, I'm just going to show essentially a drawings for what these things look like. Okay. Okay. So is everyone back with me? Yep, okay. So what we're going to do on the next few slides is we're just going to have a look at what a linked list looks like. Yeah, so in this case, this is the simple example we had where we've got the head which points to the first element, then the first element points to the second, and so on. Ad infinitum for how many items we have. Then we have the doubly linked list. So here we have a pointer to the head, and we have a pointer to the tail, and we have a count. We might have other things as well. So when we're doing an insertion, there's various cases we need to take account of. We need to take account of, well, for example, if we're inserting at the head, the order of the assignments matters, because what happens if I just go, okay, head equals new data? Yeah, we've lost the rest of the list. So in fact, what we do is we set the new elements next to the old head. And then we set the head of the list to the new element to insert at the beginning. So we need to change 2 pointers for insertion at the head. This is for a singly linked list. We've got to do a bit more work with a doubly linked list. Okay, inserting at the end. That's easy, because we just step through the list until we find the tail element. And then we say that the tail element next is the new node. Inserting in the middle, we say the new element next is the next element, right? Or what we would call as current. What would happen in a lot of these algorithms we use current and previous, and this element 1138 would be current, and the element 42 would be previous. So news next is current, and previous's next is new. To actually insert this 500 in the middle here. Okay, so now deleting. Deleting means, so we understand that one of the things we need to do as part of insertion is to allocate the node we're going to insert. So allocate this node which holds the 500. Yeah? Everyone understand that? You can't simply pass in the address of something on the stack. You need to malloc a new node and copy the data into it. because it needs to be independent on the heap from the stack. Everyone remember why it needs to be independent from the stack? Why is that? Kind of covered this a bit last week, actually. Yeah, the stack may be reclaimed. Yeah. So we want to avoid that problem. Okay, so now when we're deleting, yeah. Now this is an interesting one because there's an extra step here that I never do. I never do because it's not needed. But anyway, we'll have a look at that. So here, if we think about we're searching for the element to delete, so what happens is that this previous node with the 42, that would be previous. This node with the 1138 is in fact current next, and this 500 is current. It's the one we want to delete. So what we do is we go previous is next equals current next. So you see how, does everyone see how that's removed the 500 node from the list? Previous is next. Yes, we're going to get to that, Ross. Let's not jump ahead. All good. One of the things you got to remember is that once you free memory, you must not access anything that is part of that memory, including pointers to next and so on that are part of that memory. Okay, so now what we have is we have this here with this node with the 500. Now here's the thing I don't bother changing, is this 500's next still points to 1138. But I free it. And then I don't worry about it. Because I'm not accessing that anymore, so it's not a big deal. This person, by setting it to null, they're being overly cautious, but that takes extra time. So it's up to you. I don't bother with things where I don't do additional operations which are not necessary to get the job done. Okay, here's an interesting idea. Print list, person node, if list not equal to null, print out the data and then print list next. So we're using something here. We're using a certain mechanism here. What mechanism are we using? Starts with R. It's recursive. Yeah. We get no benefit from doing this, by the way, and don't do your list iteration like this. It's silly. It just uses up memory for no good reason. Having said that, what difference would it make if I take this line here, this print list next. So if I print list. What difference have what change have I made? Yeah, because it will do the iteration first. So it will actually iterate until we get to the end of the list, and then it will print each node on the way backwards. It's a nice way to actually be able to iterate over a list backwards when it's only a forwards list. And in fact, I'll just undo this because on the next slide I actually have that. Okay, let's see what else do we got. Okay, I'm going to spend about 5 or 10 minutes going through the person list, linked list code. And in fact, list.c is really the one I need, and so let's go from the top. Okay, so let's start off with what do we need to do for list initialization. So I set the head, so let's So we've got here in the top half we've got list.h, in the bottom half we've got list.c. So here we've got the header structure, and so what do I do to initialize it? I set its head to null and count to 0. Or even better, because remember that null is just 0. It's actually 0 cast to a pointer. So it's a void pointer. You actually find that null is actually defined as 0 cast to a memory address, right? So the mem set down here does the same thing, writes 0 bytes to the entire structure. Okay, so that's a list in it. Which is better? Well, it depends on the size of the structure, to be quite honest. If you decide to go into... that's true. And so it's actually possible for structures this small, there's probably wasteful. But if you look at, like, for example, if you go into things like, say, network programming, and there's a lot of structures which are actually quite large, but you only want to set 1 or 2 elements. So it'd be really quite wasteful and boring to actually be assigning 0 to each of these elements, which you never use. So what we do is we memset the whole thing, and then we only set those things we need to change. Yeah, so that's a good point. Okay, so now let's have a look at add. So I've got some variable declarations. The assumption here is that data has already been mallocked. Right? So that's the only assumption I'm making. Is that data has already been mallocked. So I assert, so I'm saying yes, all these pointers are non-null. So I allocate some space, and we can even have a look at safe malloc here. So what I've just loaded up onto the screen. So I allocate space, print out an error message, and exit if the allocation fails. What do people think? Do you think this is a good idea or not? I'm actually in two minds about it. The main issue, though, is this allocation failed. There might be a hell of a lot of other allocations which have been made that we want to safely free or save before we quit the program. So it might be a good idea, in fact, to add another parameter here, which is a function pointer. Which actually points to the function which actually does the cleanup before we exit. And we'll have a look at function pointers in just a moment. Yeah, that's safe malloc. Which is why, by the way, have you noticed I don't check the return value of safe malloc? But I definitely check the return value of malloc. So you should actually check the return value of malloc to check that it actually succeeded in the allocation. What does malloc return when it fails? Correct, it returns a null. Awesome. So I allocate the space for the new. I assign the data element to my new node. Something else I would do actually that may not be obvious to you, but I would do new I set news next to null? Well, it might be at the end of the list. If it ends up being at the end of the list, I don't have to set it then. It's just being a little bit cautious as a programmer. In fact, what I might do right now is drag this up a bit because I want more space for what's below. Okay. So you see, if I had a bug here, right? Because what I was doing is I was setting next. I wasn't setting next, but then for head, I was assigning new. I never actually set next. So in fact, simply by showing you a good, cautious principle here, I fixed a bug in my program. Okay, that's when the list is empty, we simply assign the element and we're done. Okay, so now while current not equal to null, so we're going to iterate over the list. We start it at the head, and when current is null, what's that mean? We're at the end of the list, correct. And now I like to actually use a comparison function. Now, I remember seeing in student feedback, which I've deliberately refrained from making any comments in the student feedback forum because I feel that's your space. But someone mentioned they didn't like the return values from strcmp, and my toes curled. Because, well, that's a standard interface. You have to get used to the standard interfaces. And one of the standard interfaces is that comparison functions, if the first element is less than the second element, returns a negative number. If the first element is greater than the second element, it returns a positive number. So it's like subtraction. Well, in Java, you've got things like the compare to interface and comparators. Yeah. So it's the same thing done everywhere, pretty much. C++ is a little bit different because it implements the less than operator, which is a bit different, but pretty much everywhere else, yeah, it's ints. So it's a comparison, it's like a subtraction. And where it comes from is from assembler. Comp is in fact the operator for subtraction in assembler. So that's where the comp functions come from, if anyone was interested in that. Okay, so let me just show you my person comp function. Okay, so I compare last name, and if they're not the same, return whatever that is. Otherwise, we'll do a comparison on first name. And if they're not the same, we'll return that comparison. Otherwise, we'll subtract the ages. So we're going to sort by last name, then first name, then age. Okay? And so we just iterate over the list. Previous is current, and current equals current next. And so when we do our insertion, we'll insert between previous and current. So now, what does it mean? Okay, if previous is null, we're at the beginning of the list, right? So then we do that whole thing where we set news next to the rest of the list and then set the new element to be the head. That's what we're doing there. So current is not null. So if current's null, what's that mean? Again, if current is null, what does it mean? We're at the end of the list. Cool. So I'll remove this because I fixed this up above, remember? Because it's one of the first things I do is actually set news next to be null. So if we're at the end of the list, we simply set previous as next to the new element. Otherwise, we probably should swap these around, but it doesn't really matter because I've got access to both of those pointers here. So previous is next will be the new element, and news next will be the current element. So we're inserting in between. I'm going to go through an example in the tutorial tomorrow of us doing exactly this from scratch. So if you're struggling with any of this, that's fine. We're going to go through it again. And then I've got an example of how we'll free the list. So I iterate over the list. I have an additional pointer here, next. And the reason why I have next is I cannot, once I have freed an element, I cannot access any of its data. So I assign next to current, and then I shift current along by one. I free next data because remember that's been malloced, and then I free next, and we're pointing at current. So we're always moving ahead by one, freeing each element and its data over and over and over till we get to the end of the list. We'll have a look at deletion in a later class. Certainly we'll have a look at deletion in next week's tutorial. Okay, so now going back to my slides. We're going to have a look at function pointers. So a function pointer is a special kind of pointer. So you know how an array is a pointer to the first element of the array. So it's a pointer to the 0th element. Yeah? but it's a constant pointed to that 0th element. Everyone's comfortable with that? Okay, so what about the idea now that a function pointer is a pointer to the first instruction of that function? And in fact, the function name is a pointer to that first instruction. And in fact, correct. In fact, you can see in some debugging information, you'll see stuff like function name plus amount, which means how far into that function are we. Well, a line is not necessarily, like a line is at least one instruction. I'm talking about the machine code. Remember, there's not a one-to-one representation between machine code and your source code. So yes, you might see it as an assembler instruction. Yeah. For example, a printf command may in fact be many instructions. And there is some benchmarks which talk about, yeah. Ha. Yeah, you know you're digging too deep when you get to that point, because essentially in this course, really, we are only concerned with the high level source code you're writing. That kind of stuff will come later. That's all good. Okay. So, function pointers take this general form where we have the type name, star name of the function pointer, and what are the parameters the function pointer accepts. So for example, int star comp, const person star, const person star might in fact be the a pointer to a function that compares persons. And a function pointer is a variable which we can assign a function name to. They need to have the same return type and same parameters. So let's very quickly have a look at this. Correct. Delegate is what's used in a language like C# for the same kind of idea. C++ has the idea of a functor, which is an object which holds a function. I think C# is a bit like potpourri. So if you take all of the ideas from all the different languages and you throw them in a bucket, swish the bucket around and pour it out, you've got C#. So I kind of feel it tries to be too many things, but you know, of the kind of modern high-level languages, it's probably my favourite. Yeah. So let's have a look at this funcpointer.c. Okay, here we go. I've declared up the top a function prototype for a comp function. But in here I've said there is a pointer to a function called bcomp, which accepts ints equals comp. And then I call bcomp, which actually calls comp, because that's what was assigned to it. So let's run that. Okay. Okay, so now let's run it. Yep, does what it's supposed to. But here's something interesting. What do you think this does? Do you think this will compile now? Aha! That everyone who said no has misunderstood something. Has misunderstood how function prototypes work. Here, this function pointer here will match any function which returns an int. Yeah. So, correct. Still works the same. But what empty brackets does not mean accepts no arguments. So if I change this, now this will generate a compiler warning, because the left hand side and the right hand side have different types. Left hand side accepts no arguments. Then we get into all kinds of hairy stuff. I'll show you this one first. So we get a warning, initialization from incompatible pointer type. So let's do that. Let's just say still, no, doesn't match. So it's only the empty which is valid there. If you want variable number of arguments, check out the standard arg.h. which is what printf uses to allow variable number of arguments and so on. Okay. Just one more thing before I leave you, and that's in yeah. I got this example here in func pointers. I'll quickly talk about this program. It's pretty simple. So I've got these different choices that a user might make, where they might print out every second character, they might reverse the contents of the file, they might shuffle the contents of the file. And I've got this function here called process, which actually does the processing of the file. And I've got this thing called, which is a Boolean pointer to a function, which accepts a file pointer, and it consts class star. Right? And then I have these functions, every second, reverse. See, they all have the same arguments. So now let's have a look at the program. So okay, I've just hard coded that there are going to be two files called input.txt and output.txt. And you see I've got an array. Do we remember what these guys are? No. What's a right func? So a pointer to a function that accepts a file pointer and a const char pointer. Right? Now in this case I've specified what the arguments are. So this is an array of pointers to functions. Yeah? And now I have an array of char pointers that explain what each function does. So then, what we do is we get a choice from the user, we display a menu, we get input from them, and then we call func's choice. Remember, that's the array of function pointers passing in the output file and the line to output. Right? And then we have a separate function that does each job. So this one here will output every second character. This one here we'll reverse the characters. We'll reverse each line. This one here, we'll shuffle the line and then output it. So, let me just... Yes, in fact, what we're really doing is we are delaying until runtime the decision about which function gets called. Every programming language has some way to do this. Like, for example, PHP has variable functions, where the actual name of the function is stored in a variable. It's kind of a function pointer, really. C# has the idea of a delegate. Java has the idea of classes that have a single function. Right? So if I run this, please select what you want to do. Okay, I want to write every second character to the file. Okay, so if I see, it's just every second character has been written to the file. If we have a look at the original input.txt, you'll notice that I tend to use lots of examples from H.P. Lovecraft because they're fun and they're in the public domain. File manip. This time I'll reverse each line of the file. This time randomize. But the key thing, right, is in this here. Is this array of function pointers, an array of strings. So the strings is the menu. That gets displayed, and the function pointers are the actions performed by that menu item. Okay, I'll leave you there because I think I've covered quite a bit of stuff, and you're going to need function pointers for the assignment, guaranteed. Although this is pretty common stuff. It's the idea essentially of a callback function. So we can actually decide which function to call at runtime based on some condition. Say, for example, a choice from a menu or whatever. Okay?